Hey, what's up? It's your old pal, Mr. Cook. We're going to go through the group work assignment, problem by problem. I might section it off so it makes a little bit smaller video, depending on how long it's going to take me to get through this first page. Okay, so first we need to graph this out by hand, so make sure that you have your graphing calculator handy so we can graph these out pretty easily. Okay, there we go. So first, you need to graph this out by hand. So, the calculator is still going to be at your disposal on the test, but to show your work for graphing out, it's really easy to, try to factor out an expression. On the test, we'll give you a factorable expression, like something that's really within your realm of, of factoring ability. So, like this one, for example, if we have x to the fourth minus 4x squared, x to the fourth and x squared, you can factor both of those values out pretty easily. So if I factor that common factor out, I get x squared times parentheses x to the fourth divided by x squared is x squared, so x squared. And then negative 4x squared divided by x squared just gives me a negative 4. And then this is a difference of squares problem now, so I can just factor that. So I get x squared times parentheses, and then and take the square root there, so I get x plus 2, x minus 2. And it's all factored out. That's all the work that I need to show for all of this work right here. Determining the end behavior. So the end behavior, you guys are familiar with that from that chart of the end behavior. You can always just graph it out on your calculator too to see how it looks. But the end behavior for this, since the degree is 4, then it's going to be positive. So the degree is 4. And then the lead coefficient is positive. So if it's plus or minus, it's a positive lead coefficient. And when you have an even degree and a positive lead coefficient, it's either going to be, up on the left-hand side, and then the graph is going to point up on the right-hand side. For the intercepts, the x-intercepts, we need to, set each of these factors equal to 0. So if I have x set it equal to 0, that's already 0, so that's a solution. So it gets me 0, 0 for an x-intercept. And then another factor that I have is x plus 2. If I set that equal to 0, then x will be equal to negative 2, and therefore negative 2, 0 is going to be another one of my x-intercepts. And then if I use this last factor, x minus 2, and I set that equal to 0, and solve, then that means I get 2, so 2, 0 is going to be my last x-intercept. Now, since the 0, 0 is also on the y-axis, this is not only an x-intercept, but it's also a y-intercept. So I'm going to graph those coordinates out, 0, 0, 2, 0, negative 2, 0. Okay, next. State any zeros in the multiplicity of each, describing their behavior. So their behavior means is it going to be touching the x-axis on that x-intercept or crossing directly through the x-intercept, the x-axis at that x-intercept. So if you want an idea of what to do for this, just go back to your quiz that you took where we had this nice little table set up where you have to find the zeros, the multiplicity, and then also tell whether the graph is touching or crossing the axis. So for each 0, the first 0 that I have is 0. Its multiplicity can be found on the factor that I find the 0 from, so x squared. Since the power is 2, that means that the multiplicity is going to be 2. And then if the multiplicity is an even number, that means that it's going to touch off the axis. So in other words, at that x-intercept, the graph is going to deflect off of it and go in the opposite direction. So that's what happens there at that x-intercept. For the next x-intercept, negative 2, so I have a negative 2 for a 0. The factor that I got that from was x plus 2, and that has a multiplicity of 1 because the power up there is 1. And then if it's an odd number, then that means it's going to cross directly through the axis. So if I have an x-intercept with a multiplicity of an odd number, then it'll just pass directly through that point, through the x-axis. The last 0 that I have is positive 2 from that factor, and then the power on it is 1, so that's the multiplicity, 1. And then if it's an odd multiplicity, then that means that it's going to cross through the axis as well. Okay, so right now we already have enough information to kind of draw out a really rough graph. It starts by pointing upwards from the end behavior. It's going to go over to the x-intercept at negative 2. It's going to pass directly through the axis. And then it's going to make it at this point. At some point, it's going to turn back around because it's continuous and go back over to the 0. And then at 0, it's going to touch the axis and turn back around. And then at some point, it's going to make its way back over to this other x-intercept at 2. It's going to cross through the axis and continue onward. So it's going to have that up on the left, up on the right kind of look to it. Let's get a little bit more accurate with our graph by finding a couple of additional points. And for this, you can just use your calculator and in particular the table. So I'm going to type in the expression that I have, x to the fourth power minus 4x to the second power, and then graph it. There's the graph for it. So it already looks like really close to the graph that we have. Let's just get a little more accurate from the table value. So second table. So just a couple coordinates in between those x-intercepts, like -1, -3. That'd be a good coordinate to graph out. And then that one at 1, -3 would work out really well too. So let me show you why those two would work out real well. It's because they're the low points right here for the where the minimum goes there, and then the other minimum over there. So that's going to be 1, -3. There we go. So now to make it a little bit more accurate and draw it in, it goes through that point to that point. It curves back around over to this point, goes back up through that x-intercept, and then goes up for infinity. The end behavior is basically what happens when the x values get really, really large in a positive direction and also in a negative direction. So are they pointing up? Are they pointing down? It's based off the graph. So that's why you can graph it out and tell how it's going to look. See how it points up to the right and then up to the left? That's the end behavior. So you can always check your work through just graphing it out too and interpreting it that way. All right, next we're going to do long division. So with long division, we need to watch out for, and with any polynomial long division, we need to watch out for it, is placeholders. So placeholders, that's what happens when we're missing a term in our sequence of a polynomial. So when we're using long division, or any type of division, placeholders show up when you're missing a term. Like I have an x to the third term, an x squared term, an x term, and then a constant. So it goes x to the third, second, first, and then x to the 0 power. So that's all good. All of those values are accounted for. But this polynomial that we have is missing one. I have an x squared, I don't have an x, and then I have a constant. So that x value that's missing is going to have to be accounted for. So we write out our polynomial like this instead: 2x squared plus 0x plus 1. I know it seems arbitrary to do that, but it helps out a lot in making sure that you keep a proper order to your division, and making sure that it's nice and neat helps out a lot when you're working through the problem. Okay, so anyways, with our division, we just put this part underneath the division bar, so 6x to the third plus 10x squared plus x plus 8. And then on the outside, what we're dividing by, so that's going to be 2x squared plus 0x plus 1. Okay, so when we do the division algorithm, what we're trying to do is turn this lead coefficient into this lead coefficient and all of the remainders as well, the same intended purpose. So to turn 2x squared into 6x to the third power, I need to multiply this by 3x. So 3x goes on top here, and then I distribute the 3x through all these values. So 3x times 2x squared gives me 6x to the third, which is what we're trying to do, make it look like that. 3x times 0x is 0x squared. Yes, even the x squared, because x times x is x squared. 3x times 1 is 3x, so plus 3x. Now when we find this polynomial, we subtract it away entirely from the three terms up here. So 6x to the third minus 6x to the third gives me 0, so it cancels it out. 10x squared minus 0x squared is still just 10x squared. X minus 3x gives me negative 2x. Okay, so that's my remainder from doing this first part of the algorithm. Now I drop down a plus 8. That's my next term. All right, now I start the whole process over again. I want to make this 2x squared look like 10x squared. So I multiply 2x squared by 5. So I put a plus 5 up there. And 5 times 2x squared is going to give me 10x squared. 5 times 0x is going to give me, again, just plus 0x. 5 times 1 is going to give me a positive 5. So now that I've found this polynomial, I subtract it away and see what I get. So 10x squared and negative 10x squared cancel out. Negative 2x minus 0x is going to give me negative 2x still. 8 minus 5 gives me a positive 3. Now, I can't make this 2x squared look like negative 2x unless I divide out an x term. So that means that this is going to be our remainder. I have to stop right there. You can always tell because you can keep dividing as long as this degree is the same or less than the degree of the value that's above it or its remainder. So since this is less than that, we have to stop here. Now, writing out our answer, once we finish dividing this out, the polynomial that we get as a result from dividing out looks something like this. So we put our quotient in front, so 3x plus 5, and then plus our remainder, whatever it is. In this case, it's negative 2x plus 3. Over whatever we divided by. So I'm just going to write the simplified form of 2x squared plus 1. You could also write 2x squared plus 0x plus 1. I'm sure that wouldn't really cause much of a problem because it's literally the same answer. Okay, now moving on to number 3, synthetic division. So we're going to use synthetic division to verify that these two x values are zeros of the given function. So to check and see if they're zeros, then that means that our remainder must be equal to 0. To make it a 0. It seems pretty obvious. So we're going to use synthetic division with these values and see if the remainder is 0. If it is, we write yes in the little blanks. If it's not 0, then we write no in the blanks. So 2 goes in the corner for our synthetic division algorithm, and then we write up the lead coefficients, or the coefficients for all these. So 1x to the fourth, 1x to the third, negative 7x squared, negative 1x, and then 6. So underneath the constant value 6, we're going to put our remainder box because that's where it is. The first term always stays the same, so it just drops down, stays the same. And now each number that we get here, we're going to multiply by 2 and put it in the next available spot. So 1 times 2 is 2, so 2 goes here. And we add straight down. 1 plus 2 is 3. 3 times 2 is 6. 6 minus 7 is negative 1. Negative 1 times 2 is negative 2. Negative 1 plus negative 2 is negative 3. Negative 3 times 2 is negative 6. And 6 minus 6 gives us 0. So since the remainder is 0, this is a 0. So that means that yes, x equals 2 is a 0. So yes, that works out there. Now, let's check and see if negative 2 works. So negative 2 now goes in the corner, and then we put the coefficients in front of, for that in the algorithm. So we have 1x to the fourth, 1x to the third, negative 7x squared, negative 1x, and then positive 6. So 1 times negative 2 is negative 2. 1 minus 2 is negative 1. Negative 1 times negative 2 is a positive 2. 2 minus 7 is negative 5. Negative 5 times negative 2 is 10. 10 minus 1 is 9. Okay, and then under the constant we have our remainder. So 9 times negative 2 is negative 18. 6 minus 18 is negative 12. Is negative 12 equal to 0? No, obviously it's not. So that means that no, this is not a 0 of the polynomial. So that's it. That's all that we have to do for the first page, and we are all done. So now let's take a look at that second page and make a video for that.